In 2013, the SAFIRE Project was created. The objective was to replicate the Sun's atmosphere in a laboratory on Earth.
Wow, look at that.
A lab was designed and built, and at its heart was the SAFIRE plasma engine, the only one of its kind on the planet.
Michael, if you guys want to turn your microphone on at any time.
Okay, we can see you and Colin. Can you see me in the background talking to you on the cell?
Today, 4 years later, the SAFIRE team gives a tour of the lab via the web to a scientific review panel scattered all over North America. Two things define SAFIRE: a unique premise and a remarkably powerful methodology. The premise driving the project is the idea that electricity plays an essential role in the functioning of the Sun's atmosphere. The methodology used to build and run the SAFIRE lab comes from the world of engineering and manufacturing. It is a statistical procedure that allows for incredibly precise control over the design and managing of experiments. This combination of premise and methodology has yielded remarkable, if not startling, results.
Comment that those last 2.58s, I would do more.
So it was 0.5, I thought.
No, 7 and 8.
The actual position of the plasmas here. Yeah, so this is SAFCON. So this test, we have ongoing video feed of the plasma. And I think we're increasing the current now. Yeah. So these tufts that you see, these balls, are actually not sitting on the surface. They're actually sitting just off the surface.
In August of 2017, the SAFIRE team presented its most recent discoveries at the Electric Universe Conference, Future Science, in Phoenix, Arizona.
Just listening to SAFIRE, and that's just the beginning. So SAFIRE has proven itself to be capable to contain, control, and stabilize high energy dense plasmas, and you're going to see that tonight. We're seeing chemistry changes. We are slowing the speed of light down. We're seeing variations in electron density comparable to the photosphere, heliosphere, and nuclear bombs. Electrical confinement of high-energy photons. These are just some of the things. And all of these things here are due to charged plasma affecting matter of a different electrical potential. So this time, I want to take the opportunity, which is usually saved until the end of the presentation because time is short, to thank the other very key members who are contributing so much to the success of this endeavor. So first of all, I'd like to thank Scott and Bruce Mainwaring for their ongoing and unwavering financial and moral support. Dr. James Ryder for your insight, for an ear to hear, and with help herding the cats. And Dr. Lowell Morgan, for your amazing knowledge and insight into the complexities of plasma physics. Walt Thornhill, for your work in the electric universe model and cosmology. And Dr. Don Scott, for your work in developing a more mature model of the electric sun. Jan Andercho, for your hard work in data acquisition. Leighton McMillan, for your hard work and the assistance in building SAFIRE in such a short time. Jason Lickford, for your work in mechanical engineering and telemetry. I'd like to thank you, Susan Sherratt, for your untiring help in administration, finance, and legal matters, helping to make this project go so much smoother. Tracy Childs, for your ongoing financial work and for always being an awesome woman in my life. Ben Gedlow, for your work and the team in pulling this presentation together. And none of this would have started without you, David Talbot, making that providential call to persuade me to take on this project. So now I would like to introduce part of our team who are joining me tonight to assist in presenting our discoveries. Please welcome Dr. Michael Claridge and Dr. Paul Anderson. Research objectives. There's a lot of detail to it, but fundamentally, SAFIRE stands for Stellar Atmospheric Function and Regulation. The objective sounds way out there, but basically the contract says we're to do everything we can to recreate a star in a jar and test the electric universe and test the electric sun model. So the technology we're going to use in SAFIRE, or have been using in SAFIRE, we have floating potential, plasma density, ion current density, electron energy distribution, electron temperature, mass spectroscopy, optical spectroscopy, thermal measurements, infrared thermography, radio frequency measurements, electromagnetic measurements, scanning, electron microscopy, optical microscopy, voltage across the plasma, current across the plasma, voltage feeding the plasma, current feeding the plasma, and video capture of the plasma phenomena. And we're going to discuss each one of these with you in detail tonight. Just kidding. What we will show you, however, is how we use this technology to reveal some of the most startling discoveries we made this year instead. Now, Michael, you're up.
I'm up.
Let's get started.
Optical spectroscopy. So Jim Ryder said everything we know is from light. I'll think about that. But almost everything we know about the sun is definitely from light. And optical spectroscopy is a really good friend as a scientist. Every element emits very characteristic frequencies. A lot, you could imagine, like every species of bird has its own song, and you would never confuse a chickadee with a seagull, right? So if you study these elements spectrographically, each one is quite unique. And we can learn a lot about what's going on for those atoms by things like the relative heights of those spectral lines, the widths of those spectral lines, the shape of those spectral lines. Here's 3 different discharge regimes in our plasma. On the left, you can see there's the center anode, very bright, and then around it is a halo. Okay, those are our double layers, a halo around that. In the middle panel, you can see that the double layer is gone, right? Just the center anode is there. And on the right-hand panel, we basically just cranked all the dials up to 11 and got a super high power discharge. You can see there, that's our spectrographic probe tip. It's a fiber optic that we can move around anywhere we want in the chamber to study what's going on. And so right there, that fiber optic tip is looking right into the double layer. Okay, it's not looking at the anode, it's looking at the double layer. The next one, the double layer is gone, so the probe tip is just looking at the general plasma discharge. And then the last one, we move the probe, but it's looking at this super high power discharge. So we'll just look at one spectrographic line. This is like one note being emitted by the hydrogen. Okay, it's the 656 nanometer line, one of the most famous spectrographic lines in the universe. And we can measure the width of that. And inside the double layer, we see the width is 0.012 nanometers. Okay, that's pretty tiny. These are pretty good instruments we have. We boosted the resolution spectrographically by about a factor of 4 or 5 just recently, so we're getting, it's good, right? That's pretty good resolution. Then the double layer goes away, the width of that line, same line, hydrogen emissions, the width goes down to 0.07 nanometers, and then for the third one, the super high power one, it jumps back up to 0.09. This made us super excited to be able to see this and measure this, because one of the reasons these lines can change their shape like this and get broader and more narrow is the number of free electrons running around in the plasma. Okay? And if there's a lot of free electrons running around the plasma, you can kind of picture that they're crashing into hydrogen atoms and causing extra wobbles on top of the note that's being emitted. That tends to broaden the line more. Okay? That may seem like a small change, 0.05 nanometers from 12 to 0.07, but that represents like 50 to 100 times change in the free electron density. So double layers have within them about 100 times more free electrons running around than not. Okay? This is super exciting that we can measure this. If you just stick in a probe into one place and you get one measurement, you're not necessarily so sure you can guarantee what you're looking at. But if you can measure changes like this, then you have much more confidence as a scientist that you're actually observing something that you can talk about. And where do we see comparable changes, in free electron density? Well, we see those changes going from the photosphere to the chromosphere, from the chromosphere to the corona, out at the end of the heliopause. So we're getting into the realm where we have changing conditions in our chamber and the ability to measure them that are also going on in our star. That summarizes that. I think it's too early to stop. Do you think it's too early? I think it's too early to stop.
I think they're just absorbing right now.
Yeah.
Right.
So we'll just take a breath and keep going?
Sure, you can take a breath, I'll keep going.
Okay.
It's not always this much fun in the lab. There's a lot more yelling and screaming going on and things like this. So the next section is where we get into the fun part, statistics, okay? But it's really, really important because design of experiments actually is the mainstay. It's the foundation of the work that we're doing. Because in science today, there's a lot of stuff that's in question, and we're not going to be subject to those kinds of questions. So we impose what's called design of experiments, and Dr. Paul Anderson is going to take you through what we've been doing with SAFIRE. And I think you're going to be amazed about some of the findings we've done.
All right. Thank you, Monty. So just as Monty said, we wanted to investigate some basic plasma physics that is occurring in our chamber. The first thing we did was, in looking at our chamber, was that we wanted to tame the plasma. Okay. Now I'm going to show you first a video here of the plasma as we know it now. We can move the cathodes, as you can see. We can stabilize double layers. We can change the double layers as a function of distance. At the same time, we can also change gas concentration and type of gas in there. It wasn't always that pretty. Some of our initial plasmas were pretty dirty, very unstable. If you look at a lot of old plasma literature before they even named it a plasma, they commented on how difficult it was to contain this energy and understand it. So these are some of our initial discharges, lots of impurities on some of the materials that we use for the anode, striking different discharges, a lot of instabilities in the plasma. And what we eventually wanted to look like this, right? This is a very simple plasma, which entails a simple anode on the left and a cathode on the right. And this is basically a 1D plasma where you're striking a discharge between these two electrodes. You can adjust the gas pressure, the gas type in this, as well as the voltage in this system. Fairly straightforward. This is a top view of SAFIRE. It's not as straightforward as the plasma tube. This is looking down on SAFIRE from Monty's model here. And as Monty listed in previously, all the instruments that we have them there for a reason. And in every single run, we use all the control instrumentation for the chamber, as well as driving all the detection that Monty mentioned. So there's a number of detectors on here, as well as the fundamental control of the chamber. So through a lot of data acquisition and controlling, we're able to now control that plasma chamber and carry out experiments. So one of the first things we had to confront is how to drive it and understanding the gas input. Like, this is just one aspect of the gas input here. This is the gas and vacuum control system. We also had to understand our SOPs to implement safety procedures when you're working with 2,000 liters of hydrogen at high temperature, right? So we had a number of things to control in addition to wanting to control the plasma. So we looked in the literature and we talked about it, and we said, okay, well, learning to drive this, let's concentrate on plasma experiments that are well documented. And that's why we came up with Paschen's Law. We decided to choose Paschen's Law to understand the plasma ignition in the SAFIRE apparatus. So Paschen's Law describes a point of current flow at a particular electric potential through an ionizable gas or gas between two electrodes. Okay? So fundamentally, we have two electrodes, positive and negative. You have a gas. You have a certain pressure of that gas, usually conducted under vacuum. And you have a distance between those electrodes. And you strike a voltage. And there's no current flow initially until you get to a certain point where that voltage can overcome ionized gas and conduct a current. Now, when that occurs is a certain voltage. Okay? So we decided to do that in SAFIRE. So this is a classic Paschen curve in hydrogen. The other gases also have other curves that are very similar. They exhibit the same minimum. So if you notice here in the graph, our x-axis here being a term of PD, pressure and distance. Notice it's in a logarithmic scale. So it's a reduced variable, so you have both pressure and distance in one axis. And in our y-axis, we have our voltage that we strike to obtain a discharge. So if you go ahead and do a bunch of plots at different pressures, at different distances, you'll end up falling on a curve like this for your electrodes. So what we did in SAFIRE, we went ahead and did in SAFIRE apparatus with a spherical anode and our two cathodes at various distances, equidistant. As much as we wanted to vary both of them, we kept them constant. And we discovered already SAFIRE is acting very differently than a typical plasma discharge apparatus. We had to use a modified version of Paschen's curve, which you see there, of the law. And we also found that the gamma term, which is in that lower denominator in the denominator, that did adjust with different distances. And so that's something new that we're exploring, and we hope to get a publication out of this. So you'll notice that already we have a departure from regular plasma physics in a regular anode cathode discharge in, say, a discharge tube. And another reason why we did this is, okay, we ignited the plasma, but what is the morphology of the plasma? What does it look like at these various settings? So it's kind of an experiment with killing two birds with one stone, in that we determined the ignition characteristics which we needed to control the plasma, and we also explored the morphology of the plasma, right? So that was a very powerful thing. We were able to pursue some various regimes and then establish our design of experiments. So we discovered that the configuration, it's a significant departure from typical plasma apparatus that you may have from a typical anode and cathode. So then we went into the design of experiments. We decided on where we're going to look, what kind of plasma regimes we want, because ultimately we want to dial in stability for experiments. There's no use in doing experiments for double layers if they appear for 1 microsecond and then go away. We wanted them nice and stable. Now, to obtain stability in any system, whether it's in SAFIRE or whether it's in your kitchen baking bread, we need reproducible results, but that only comes from understanding your factors. Factors is another word for variables. So to understand those factors and variables, you need more experiments, right? Traditionally, this is called the Edisonian approach. You have more factors, you do more experiments, you get more data. The problem with that is that just because you do more experiments, you might not be increasing the resolution. In other words, the signal to noise. the signal to noise that you're looking for. You need to increase that signal from the noise so you get reproducible results and you know you're stable. And what design of experiments does, it's a methodology. It increases the resolution, but it also decreases the number of experiments you have to do. So I urge many of you who are experimentalists or who are curious to look up design of experiments and to learn the techniques, because it is extremely valuable in both saving time and resources, and it greatly increases your resolution. Now again, I won't go into why that is. I discussed a little bit of it in my past presentation, and you can read about it online. But basically what you're doing is you're conducting experiments where you're making sure your points are orthogonal. So in other words, two factors are always opposite each other, and you're making things symmetric in your design space. Just an example of what that does for you, on the right column here, you can see the efficiency. That's a measure of the experimental variance. You can actually calculate the variance in your experiment prior to even doing experiments with your design. Now, OFAT stands for one factor at a time. That's how traditional experimentation is done. That's how the Edisonian approach is done. And so you can see here it's comparison between a traditional number of runs, where you're kind of a shotgun approach to experimentation, and what's called a full factorial DOE. There are many types of DOEs out there, but this is just the most basic taught DOE. And you can see that just with three factors, right, say pressure, type of gas, and distance of the cathodes, right? That's three factors, three variables. With the number of runs for OFAT, you need 16 runs. That gives you a certain experimental variance or efficiency of 2. But you're half that number of runs with your full factorial DOE. And as you get upwards, now you still say, wow, well, 128 runs, that's still a lot of runs, but there are as I said, there are other DOE formulations that you can pursue to help with this, to help decrease that number more and still maintain that experimental efficiency without having to do 512 experiments. So in a nutshell, that's really what DOE is. We explored this first in phase 1. This is our phase 1 setup. Very simple. We had an anode in a bell jar surrounded by a cathode. We had a voltmeter. Did have some other instrumentation crammed in there. But for the purposes of this was just a snapshot of one of the bell jar experiments with a small anode. And really what we determined through design of experiments is these various regimes that the plasma goes through. So we were already kind of dialing in the anode even in a small bell jar, so logic would assume we could do that when we scale up as well. And actually it does when you use the right approach, when you use designs of experiments. So we were really happy with our various regimes. This is a snapshot of, I would say, the main regimes we work with. That's not to say that there aren't others in between there. So I'll just go through here a little bit and show you close up. I call this a dark quiescent phase. This is right on the edge. Very small changes here. This is not stable. Very small changes in either voltage or current can lead to this extinguishing. But there is still a plasma layer around the edge of the anode. Now, as we increase our current, we obtain what we call tufts. These are anode tufts. These have been experimentally seen before, but we can now control them. We can control the number, the concentration in a square area, and they're always equidistant from each other. Okay? And as you increase the energy and as you increase the current in the system, they start to grow in size and also squeeze together until you reach a point where they actually start to coalesce. And this is what we refer to as moving tufts, right? This can also be adjusted in terms of pressure and current. So as these things start to move, they actually spin more, and eventually what comes into being is this double layer phase. Multiple double layers that are controlled by current and gas pressure. So this was probably the most double layers we obtained, I would say, with a 3-inch anode. This is a 3-inch anode. This is a 3-inch anode, so those tufts, I think we reached up to about 7 or 8 tufts, at least in the design of experiments that we got.
Yeah, they're about this big.
So, and they're stable. And also we have quiescent phase. This looks familiar, doesn't it? We even got some holes in that arising from something. We don't know. All right? And that layer is fairly significant. It stands off the surface of the anode. And we also have these asymmetric double layers that occur over time. Time is also a factor, but we weren't able to quantify it yet. Because what happens over time is your anode heats up. Thermionic emission happens. It changes the properties. So that's the one factor that we have to dial in a little bit more, is we don't understand the effect of time on this anode yet, but we know it affects it. And also, the ZAPM high intensity kind of let it loose phase. So those are stable regimes. All right. So to dial in the plasma also, we wanted to work with different anodes, different size anodes. The top is a 1.5 centimeter anode. The bottom is a 3-inch anode. And you'll notice that we're obtaining the same regimes. A little bit different shapes, but for the most part, we're getting the same numbers and at proportionally the same current. And what do I mean by proportionally? Well, when you're impinging a 1.5 centimeter or inch anode compared to a 3-inch anode, the current density is a lot higher on that, right? So we had to adjust our current density properly to obtain the same response. So that's what we did in this experiment. And these are just some numbers if you want to have fun with the numbers. We're calculating, but we're getting about 85 watts per square centimeter in the top discharge. But you can see in the bottom one where we throw in 22 amps, we're getting a little bit less wattage there with the calculation, but within error, you're almost there. So we're tracking very well with scalability of the plasma between different sizes. And as you can see, the current is the main driver. That's what has to be adjusted. Now, we say here, you may say, indications of a transformer. Well, that's the only way, that's why we have in quotes, right? Transformer. So as double layers form, plasma resistance decreases and current flow is less impeded. Michael alluded to that earlier. Electrons are more intense or more concentrated in these double layers. Why is that? We'll have to study some more. But now is where we get into our statistics. What you see on the graph, this is an actual by predicted plot. This is what comes out of design of experiments, okay? It may just look like a straight line to you, but this is very powerful because what it enables you to do is to predict things, okay? So the top graph here has, as you can see on the y-axis or the vertical axis, okay? Thank you. On the vertical axis, you have voltage actual. So that's the voltage we actually measure. And what do you see here? Voltage predicted. Okay. So when you read papers, scientific papers, or any kind of reports that have prediction values, that's what they're referring to. They're building a model, and they're seeing how well the model can predict the voltage, or whatever response they're studying. So we can look here that the equation of the line is pretty darn good, considering the fact that we're working with a plasma. Okay. It's an R squared. I go by the R squared value is about 92.92. You look at the error, it's only plus or minus 10 volts in that prediction. Okay. We had a number of responses or a number of observations in this set of experiments, 31 experiments. Okay. So we have sufficient degrees of freedom when we're only looking at 3 or 4 factors to determine which of the factors do what. Right? We want to know, is pressure a factor? Is the number of double layers a factor? Is current? Right? And that's what this is. So you can see here the green circle. The parameter estimates are what you'd back out of statistics. That tells you the most important factor in your model. And what is this telling us? It's telling us the pressure is actually a pretty darn important thing in this design of experiments. So your pressure is leading to significant changes in your voltage. Kind of makes sense, right? Followed by your number of double layers. Now, double layers, and we're struggling with this right now, double layers can either be a response or it can also affect the system. Just like V equals IR. The typical Ohm's law, V equals IR. What is your response and what is your factor? It depends on how you set up your measurements, and it depends on what you're measuring. So our current, though, is also an important factor, as you can see there, parameter estimate of about 10. But you see these other things down here. The pressure is multiplied by the number of double layers, and the number of double layers is multiplied by current. These are what's known as second-order interactions, higher-order interactions you might hear. And what that means is that they also have an effect, and they're needed to explain the model. They're significant enough to be needed to explain the model. Actually, I left this last one in here. You see that's 0.14 p-value. P-value is a measure of statistic that when it's below 0.05, that means that that parameter is significant. It's real in the model. You should definitely include it. So that one's 0.15-ish, and so that's not a significant factor. I just left that in there just so you could see. But all the other ones are significant. They're below 0.05. So pressure exerts the largest effect, followed by double layers. And the second-order interactions decrease that voltage response, okay? Again, what happens? What can we do now with that? That's just a bunch of numbers. How do we visualize what happens in a dynamic system? And that's where modern software and modern computers come in, because it enables us to do these designs of experiments. So as we create double layers, what you see here on this graph, you have 3 factors, which are your x-axis, which you can vary now, because we have a model that's about 92% accurate, okay? And we also have our voltage, our predicted voltage in our system. So as we change these factors, we can observe what happens to the voltage. So if you keep your eyes on the number of double layers, I'm going to increase the number of double layers here, all right? Now what happens to the other curves? Their slope changes, right? Okay. I'm going back and forth here. So if the slope changes, that means that there's a second order interaction. There's a higher order interaction between all these factors, okay? What it also means is that this model says that if we change our current or our pressure, does the voltage change? No, it doesn't. Okay, according to the model. Now, one statistician said, all models are wrong, but some are useful, right? So that's where we're at right now. But you can also see something else. You can see the unfortunate area here. That says, hey, you've got to do more experiments there. That's a confidence interval. It doesn't have enough data to give you a smaller confidence interval. So this curve could actually come down a little bit, right? As long as it's within the confidence interval. But that's the power of design of experiments. You wouldn't be able to plot this out if you were to do one factor at a time, shotgun approach, okay? So again, this is, I changed another factor here. I decreased the current so you can see the spread in the confidence interval across all these guys here, okay? So we have a little bit more work to do. That's the end of kind of plasma physics and stability and spectroscopy. I don't know, you feel like keep it going, or you want a question and answer session for a little bit, or?
Okay.
Let's move on.
Let's move on, yep. Oh yeah, here. Well, predictions in thermodynamics, like Paul was saying. What'd you say about models? Please.
All models are wrong, some are useful.
Yeah, all models are wrong, some are useful. I stood up here 2 years ago. We spent a lot of money developing and designing SAFIRE, predicting the kind of thermal responses we get out of this, because we knew we had a lot of energy of 180 kilowatts is what the design was predicting at the time. And the thermodynamics model is based on what's called total heat flux. So you heat up the core, okay, and I'll show you a picture of that. Well, the thermal response is 120 degrees Celsius, but basically we heat up the core and we put a certain amount of energy in there. It heats up the gas and other things start to respond. But the final response, based on the design, is 110 degree chamber temperature. And the temperature in and around the core here, I think I can do this. Can I do this? Oh, there it is, right around here. Would be about 2,500 degrees Celsius. And this also is telling you how fast the gas is moving. It's moving quite slowly. And that's what we were predicting. Now, the people that are working on this would be guys like Dr. Lowell Morgan, Tommy Mello, who actually develops the coding for what's called computational fluid dynamics. This is really high-end stuff. It's stuff that we use to develop, that's used to do analysis on, like, say, rocket engines and jet engines and so many other things. And we're very good at what we do. This is how we kind of make our living. However, you're going to find out that our predictions were wrong. So we did another model, and this here, what you're going to look at here, right in this area here, this is our analysis of putting in one of our probes and see what the kind of thermal response that we get. And what the model is telling us is that the temperatures of the gas just off and around the surface of the anode should be around 23 to 2,500 degrees Celsius, well within the constraints, or you might say the operating limits of tungsten, which is what the tips are made out of, Langmuir probe tips. But what really happened and I'm going to want to watch this video. I'll show you here. What you're looking at here is the probe tip, and we're going to play this video, and this is a very low powered plasma. So, this is where you say, now you see it, and now you don't. Langmuir probes are about $8,000 a pop, and I had to make a telephone call because we pulled it out. Before I get into that, I just want to let you know the actual power at that time was 182 watts. That's a 182 watt light bulb, imagine, okay? And we're going like, what is going on? So when we opened up SAFIRE, we discovered what was left. And this is what the tip looked like after it vaporized with, this is just the residual tungsten you see here on that kind of nodule. That's what was left of it, and everyone knows anything about tungsten, it takes about 6,600 degrees Celsius to boil it. To vaporize it, you need more energy. And in thermodynamics, as some of you probably already know, there's a time domain associated with it and how much heat is lost in the system as well. So it's not just 6,600 degrees. If you're going to vaporize it that quick, it would typically point to temperatures that are much higher than that. And not the 2,300 degrees we predicted, because, you know, the tungsten should have heated up, might have started glowing a little bit, but it should have lived in there. Well, obviously, it didn't. And this is what a tip looks like on the top, before and after. Now, the white stuff is alumina, and its melting temperature is about 3,600 degrees Celsius. So, I made a call. Actually, I should back up a little bit here because I got a story to tell you. I called a company who are a great company. You know, I'm not going to mention who it is. We had gone into great detail with them as to what kind of plasmas we're going to get, and they said, we have the probe for you. And so we bought 2 of the probes, and we put the one in, and I showed him, you know, we talked to him, he said, well, this is what happened. We showed him what was left of the probe tip, and he came back and he said, your plasma's too hot. I said, really? You think? You guys, I said, I told us you guys knew and understood the plasma we have, and we went over this with you guys in detail. And I'm thinking, what am I going to tell Scott? Okay. Then these guys say, let me know when you'd like to buy a new one. So I called Scott and I told him we just vaporized the Langmuir probe, and we did it with only 182 watts, and we don't understand what's going on in SAFIRE. It shouldn't have done this. And Scott says, wow, you know what that means? I'm thinking, I just lost my job. Yeah, it means that our thermodynamic modeling is wrong. I'm thinking I'm out of a job. And he says, well, yes, well, maybe. But what's amazing is it means that you have a lot of energy impinging on the probe tip. You might have an effective way of boiling water. And then he says, in his deep voice, do it again. I'm thinking, so we're all gone nuts. The guy just said, my plasma's too hot. The boss is saying, do it again. And I'm thinking, I'm going to have to spend another $8,000 on probes. These things, like 8,000, I said $8,000 a pop, we got to get control over this thing. Because otherwise, you know, we're going to burn through money pretty quick. So we decided to make a new one. Bigger, stronger. I'll put higher pressure nitrogen into the core and cool the core and make it all out of a ceramic to withstand the temperatures. It's going to work. So that's it. That's the new and improved Langmuir probe, much bigger, thicker tip. We figured that, okay, since the plasma is so intense, we don't have to worry about the small wire. We'll put something in thicker and see if we can get some measurements. And what really happened? Again. So I'm going to play a video here, and this is where we got some serious questions and Lowell got involved. just watch what happens here. This is a macro lens. Everything looks wonderful and good. We're happy.
Adios.
Ouch. Yeah, that's what we said. Well, it lived so far. That's good. Let's just keep it going. Let's see if we can... the motion that you see in a probe is from the forces that are in the plasma. And then it really did some amazing stuff. So we were happy. It actually survived. But the thermonic emissions, as we're going to get into, that's what you call thermonic emissions. That's not, you might say, the plasma. The plasma's gone out by now. So this is just a radiation. This is like when you light up a tungsten light bulb, this is what you get. So the radiation here just grows immensely. We don't know right now why the color changes. We know that we're getting other emissions in here, probably from the tungsten. And this is happening in like nanoseconds. So we go from this beautiful violet color to these colors. We don't know what this stuff is that's flying around in there. We think it could be copper and or iron or whatever. We were able to capture some of these images. But we would have to say that the atmosphere in SAFIRE is somewhat hostile. And what was interesting is the crater on the side of the anode. So we decided, well, you know what, let's take a closer look at this thing, because we were still getting information back from the tip, which is good news. And so this is what tungsten looks like after it's been machined with diamonds. Okay, it has a kind of a sintered look to it, powdery look. And this is what the tip looked like after we pulled it out of the chamber. So we've seen some cracking with the alumina a little bit. We weren't too concerned. The bright blue color was kind of interesting. But we looked at a closer look at the tip, and we see the grinding marks from the diamond wheel. We didn't see any physical deterioration of the tip, and that was just great news for us. And we thought, okay, we've got something that looks like it's going to survive. And we took a look at the alumina, and it looks like it was starting to melt, so we knew that the temperature was around 3,600 degrees, maybe a little hotter, but still in good shape. And then what I did is I just took my pliers, and we changed the probe up. We just retained it, put my pliers in to pull it out, and it crumbled. And if you know anything about tungsten, it doesn't normally just crumble. And I thought, well, we've got a bit of a problem here. So I put it under the microscope, and I looked at it, and I said, gee, that doesn't look like tungsten. Comparatively to the two, there's been a huge change in its structure, but not on the outside. The surface on the outside just looked like it was when we put it in. So we started taking a closer look at this, and it was like, what is all this white stuff? And you can see the fracture in the tungsten is very sharp. It's very clean. It's not like we bent it or anything. It just broke. So we decided, and this is when Paul got involved. He says, listen, I know some guys down at the University of Toronto. Let's get this thing in and get some scanning electron microscopy done. So we did. And I'm going over the material in the tungsten. If you know anything about materials, what you're looking at here, well, the black stuff could be contamination. But the kind of geometrical shapes that you see there above that other stuff that looks like shale is tungsten. It looks like it was getting melted. That shale isn't how it normally looks, but this is on the inside of the tip. On the outside of the tip, it wasn't being affected at all. Not at all. When we did the scanning, when we did the SEM, it was coming back that it was tungsten. The molecular structure, the crystalline structure looked just like it should. We looked inside, and this is what we found, and we found a lot more. So we took a look at the anode, that big crater that was left on the side. It was some interesting stuff. It was kind of like, okay, it was an intense plasma discharge, kind of steel material. So we thought, okay, this is kind of like, it's really cool artwork. We didn't see anything that was kind of, too outrageous. We saw this area here, and I thought, well, let's take a closer look. I don't know why, I just picked a spot. And I thought, what the heck is that nodule in the center of the top of that mountain that's in the crater here? And this is what the scanning electron microscopy showed up. Now, if you know anything about this, when you have really bright spots in SEM, it usually means that you have really heavy materials in there, heavy elements. And they start to emit. So now I'm going to hand it back to Paul, and he's going to go through SEM and tell you what we found.
Thank you, Monty. So, scanning electron microscopy. There's also an additional technique on here. Energy dispersive spectroscopy. And what I'll do is I'll show you a quick slide on where that energy dispersive spectroscopy comes in. I should have had a slide on the scanning electron microscope as well, but if you picture just a regular optical microscope that you can find, you look through the top and it goes through a series of lenses. The light comes up from the bottom through your sample and you can see it. And really the way an SEM works is that you replace your eye with an electron source, an electron gun, that gets shot through a series of magnetic lenses, which then hits your sample, which is mounted, and again, this happens in a vacuum. And then a detector is off to the side to detect the electrons that bounce off your sample. So not only do you get a secondary electron image, if you will, an emitted image, but you also get other stuff coming off of that as well. So if you have the right detectors in your electron microscope, you can detect other things. And in this case, energy dispersive microscopy is where the beam hits the material and more of the inner core electrons get excited and then relax back and emit the X-rays. Okay? So you see these characteristic X-rays, just a depiction of an atom. That electron gets excited, gets bumped off, and then relaxes down and emits that characteristic X-ray. So each element has a fingerprint, much like spectroscopy that Michael was speaking about. This is another technique to look at elemental quantities in materials in an electron microscope. So clean iron, this is just the iron anode. We're going to look at both the iron anode as well as the tungsten tip here. So what do you get from clean iron? You get a slide here where this is the probe tip. You can adjust that to be a line graph or an area. You can integrate over an area. In this case, we were just looking to see what was there, so we did the probe tip. And you can see that the composition, the oxygen comes from surface oxygen absorbed on it. You have your silicon and manganese as well, which are impurities in your iron, but mostly iron. You can see there almost 98% iron. And you get that from these characteristic X-ray energies. These energies are in kiloelectron volts. And again, each atom, each element has a characteristic series of frequencies that it will emit at certain electron impingement energy levels. So another clean iron spectrum, did a series of these just to look, kind of get a feel for the average here. In this case, there's a lot of oxygen on this one, which is not too surprising. Sometimes you get lots of oxygen. So going back to Monty's original optical spectroscope, here, you can see here this nodule and the secondary electron image here. You can see this lighting up. It can either be heavier, it can also be something that doesn't conduct electrons very well, so it brightens a lot. It can emit electrons. It charges. So what Monty did actually, Monty did all this microscopy here. He put the probe actually on that nodule first, and what do we see? We see some of these other elements here, namely aluminum and oxygen, a lot more oxygen. So that's kind of in line with aluminum oxide. It could be something from the probe. It could be something, some dust particle from the probe that's embedded in there. But there's also these other elements here. We saw manganese before. There's titanium. And there's also cerium. Cerium might be an impurity from that probe housing. But then when you increase your magnification, you go to look at the morphology of the crater around this material. It gets a little bit unusual in that we are finding barium, significant amounts of barium. We also saw the other materials as well that you would associate with the alumina from the probe tip, but it's also dispersed in that crater. But nonetheless, a lot of elements there that weren't originally there. Now in the same way, we can look at the tungsten probe tip. And we look at the clean probe tip, aluminum and silicon, probably from the housing, right? It's got alumina around the actual metal. We also detect sodium and potassium. I put a question mark because that could come from contamination, it could come from whatever the preparation was. And then we have terbium. Terbium? That was also a shoulder peak on a few of these, so it might be peak overlap, or it could be real. We need higher resolution. Then we start to see some other elements here, such as cobalt, tin. Copper is probably from the cathode, but this is the inside of the tungsten probe. So it could be contamination, or it could be there from other mechanisms. We don't know. We got to do more experiments. Electron microscopy is very selective. I spent many years doing electron microscopy, and you can find anything you want in your sample to make your professors happy. Not that I did that. But I was very careful because that's exactly what they taught me. They taught me, listen, you don't just take a few pictures. You got to take a lot. You got to go through it so that you're representing your sample honestly. And that's something that we did. We looked at a lot of parts of this. We still need to do more experiments. One set of experiments is never enough, especially when you're doing elemental analysis. So obviously we need some more verification, and we got to think of where these impurities could come from. But looking back at this micrograph, you see that this area here is sintered. Now, as a reminder, like Monty said, the melting point of tungsten is around 3,600 degrees C.
6,600.
36?
60,
melting.
60,
melting.
Oh, melting, right.
Melting, yeah.
Okay.
Boiling is 66.
Right, yeah.
Now, our anode was only at 1,000 C-ish. So we have some temperature disparities here. We also have sintering of the material. We have our stress fractures here along the grain boundaries, and we have this weird sintered kind of explosion from the inside of the matrix. So again, impurities, maybe, calcium, aluminum, could rise from aluminum materials. As far as we know, there's no barium, cerium, titanium in the chamber. You can look at all the materials that go in. The next step is looking at the processing of the materials we use. Maybe there are impurities in the materials that we use. Highly likely not, because a lot of these materials are very pure. So we know it's in chambers, we know there are impurities. We got to see in this analysis, we see something that is not accounted for. Now I'll go to a limb here. I mean, there's a lot of data out there, and take it for face value in the low energy nuclear reaction community that has done a number of studies on transmutation. A lot of the craters that they observe and that they see transmutation occurring in have the same kind of characteristics. They actually come out from the lattice of the material. Now they work a lot with palladium and platinum and noble metals that are highly loaded with hydrogen. So they load these things up with hydrogen, and then they observe these reactions that occur over time, and they're very minute, very, very small changes in the overall concentration of materials. Nonetheless, they are real, because they can pinpoint these craters, they can analyze the materials they're in, and they see these changes happening. So these are just a few select papers, some recent ones that came out with some transmutation reports. And commercial enterprises have repeated this as well. Mitsubishi and recently Toyota replicated Mitsubishi's studies here with some of their R&D investment, seeing that there is transmutation in certain complexes. So validation of results, as I said, one data set isn't enough, especially when you're dealing with certain kinds of reactions. At the University of Toronto, we're going to follow up using, this is a mouthful here, laser ablation inductively coupled mass spectrometry. So that's pretty much the SEM, but now instead of just doing a probe and looking at the X-ray energies coming off, you're actually going to laser ablate or laser vaporize materials that are in certain areas that you highlight. That is then analyzed with a mass spectrometer, a very accurate mass spectrometer. So this was a technique that the Toyota folks used to validate Mitsubishi's results, and we'll hopefully eventually return and do augmented studies on not only the anode, but possibly other parts of the reactor. So we're about to pause now again, if we want.
Yeah, go ahead.
Yes,
Yes.
sure.
You need the microphone. You need the microphone.
We know that in the sun what happening, the nuclear reaction that happens is hydrogen is the main fuel in the top and reach 1,000,000 degrees, you know, in the solar corona. So what is you aim to, what temperature you aim to reach? And the container, what kind of container? Is going to be magnetic container like the one that they trying to use now?
We're going to talk about that because the temperatures that we're seeing right now, there are two responses. And why I was talking about the thermodynamics is because right now standard thermodynamics cannot answer for why we're getting some of these, what you would see is what we call thermal responses. So think of your microwave at home. Actually, the energy you're putting in there isn't thermal like your convection oven, but you can still heat up materials that are in there. So the kind of energies that we're going to be getting into, we're going to be talking about this very shortly, would be analogous to that kind of thing. So temperature, oh boy, that's a whole discussion, and we can get into what temperature is in the context of a plasma physics, which isn't, you might say, standard thermal or black body radiation kind of responses that you get. So the temperatures that we're seeing here would be, looks like we're looking at orders of magnitude beyond what we predicted in layman's terms. But in real terms, it's not a thermal temperature in that context. We're going to be getting into this. Okay, another question?
Well, presumably you were going to use your probe to test different things, but then your probe got destroyed. Does that mean you've been kind of sidetracked and to figure out what's going on to the probe before you get on to what you're going to use the probe for?
Well, we have, obviously, if you want, you have to look at the failure mode to determine what it is you're going to be doing next, and we're already looking at that. So what we take a look is the actual time component that it took in order for this to happen. So the amount of time it took for the probe to see this much damage is about 15, 20 seconds, which if anybody that knows anything about TIG welding, that's not a very long time, because normally some of the arcs you get in TIG welders, and this is the type of tungsten we're using, you can weld for half an hour or maybe even an hour before you have to take the tip out and grind it. But we weren't seeing any deterioration on the tip. This is internal. We got big questions here. This shouldn't be happening in that context. So those temperatures in some of the TIG welding, the arc itself can reach 19,000 degrees. See, so we could be seeing the responses that we're getting here are indication of much higher temperatures. So now what's that mean? Well, we did get the tip in, we did get it out, and it was in one piece, and we were still getting data. So what we have to do now is come up with a way to get a controller that as we move it down through those double layers and back out again, we can collect the data and bias the probe quickly. We're talking milliseconds, and grab that data and get the heck out of Dodge, you know, before she gets smoked. Okay, that's what we have to do, and that's not going to be easy, because you get into floating potentials and other types of technologies, which is to do that it's going to be some challenges.
One more?
One, I think, yeah, okay, maybe one more.
Quick question. Hang on.
Might be a quick question, may not be a long, it might be a
Exactly. I love when they
long
say
answer. Yeah, I know.
It's really quick. As a control, did you look at the probe by SEM before you, I know you looked after, but did you look before?
Yeah, we have one shot of the probe tip in there of the standard tungsten, like I showed.
You did SEM on it, and you didn't see any of these extraneous elements.
No, we see tungsten. We
I
didn't.
know.
We didn't show the graph, but I did do it.
Oh,
Yes.
you did? Okay.
Yeah, it's
So
just.
you have a control then?
Yeah, we use. There's different types of tungstens you can get with thorium and a bunch of other types of elements that are in there. No, this was just pure tungsten tip. So, I mean, 99.5 or 9% tungsten. Okay, let's move on. So now we're going to get into the measurement of the plasma and double layers, the data that we were able to get from the probes once we got them to a place where we could use them. So we found, quite by accident, what appeared to be a small voltage drop just off the surface of the anode. And according to our research objectives, we were supposed to find, but it wasn't much at all. We saw initially about a 30-volt drop just off the surface. But it got us to thinking that maybe the probe tip is just too long. And So these are the double layers, and this is not scaled properly, but just to show you how it works. So the tungsten tip that you see there between the two red marks is the length of the tip that's exposed to the plasma. And that's actually what picks up the electrical characteristics of the plasma that's measuring in. So as you can see right here, between the two red lines, there's a few double layers that are in there. And what happens in effect is that because the tip is long and it's measuring through those few double layers, we think what we get is more of an average of what the voltage is. It's measuring across those. So we decided, well, let's just shorten it down. And so we did. And when we did, basically, this is what we saw. And the voltage drop here was almost 300 volts. It was 270 volts, I think, or something, wasn't it? And the distance was over a distance of 0.03 millimeters. It's really thin, okay? But it's a very powerful double layer. So we've done the test a number of times, and we validated this particular measurement, this sharp voltage drop. The actual curve coming off the back can vary a little bit, but the sharp voltage drop that you see here is typical of all the plasmas we're seeing in SAFIRE. So we can confidently say today, in fact, there is a sharp voltage drop that Dr. Donald Scott predicted. And that is, in fact, what we're seeing here. And it's pretty big. So with that, this is where Michael's going to take over, because he was doing some analysis on this, and this is getting into his area of expertise. You get all the fun stuff.
I do. So we can look at global properties of the plasma, the discharge, electrical properties, or we can also look at properties at a particular point in the plasma. So what Mani just talked through with the Langmuir probe, that's because we're trying to get measurements at particular points in the plasma. But it's also worthwhile knowing and analyzing what's going on with the discharge as a whole. So here's plots of current and voltage across the whole discharge. And you can see in the bottom some pictures of what's going on in the chamber at that point. So at point A, we have a pretty quiet discharge with a few anode tufts on there. Then we crank up the current. What happens? The plasma responds by increasing the voltage drop across the plasma and by creating a lot more of those little tufts and actually eventually sending them into motion. Then at point B, you can see that red line shoot up again. That's because we cranked the current knob. So we pushed more current through the plasma. And in response, you can see the voltage goes up again across the plasma, and we create a lot of double layers, 6 or 7 double layers there. That wiggle in the blue line, we don't know what that is yet. That's not our power supply, so to be looked at later. And I'm not actually going to talk much about what happened at the end there. We had a big release of energy, but I can't talk much about what was going on there. Okay, then you can also look at the resistance across the chamber and the power consumed by or transformed by the discharge. So the green line is the resistance across the whole discharge. Okay, and the black line is the power consumed or transformed, and it's those same regimes, same A, B, C, and D. So that first thing that happened when you created all the little tufts, that green line drops way down. That's the resistance of the plasma. It goes way down when those tufts are created, and there's that initial increase in the power consumed. Then at point B there, crank the current more, the resistance goes down even more as we're creating double layers, and the power consumption goes way up. So the plasma is responding to how we're pushing it. And one of the ways we can repeat again, and we need to study more, is it responds in ways to lower its resistance and greatly increase the amount of power it can transform. Okay. We designed SAFIRE to be able to vary voltage and current independently. This particular run, we were just varying the current. But no one knows yet in a cosmological setting what the driver is, whether voltage primarily drives things or current drives things, right, or some combination of them. So we have built in the flexibility to control them independently. And this may seem like basic research, But it is, and it's so needed, because even though we know double layers are everywhere, they're over our heads right now, they're in the magnetosphere, they're in solar flares, etc., there's not that much known about how to write down the circuit diagram for double layers in astronomy. There's almost nothing known about that. And so this research that we're doing here is largely to help give direction to future astrophysicists so they know what to look for in magnetospheres and solar flares, etc., and how to interpret what they're seeing in terms of electrical circuitry. Okay, this is absolutely fundamental what we're doing. So let's switch then to the point measurements. Okay, so now we're not talking about the global plasma, we're talking about that point where the Langmuir probe is. And when we go up close, the left-hand side is close to the anode. The anode actually starts at the number 1, not at 0, the surface of the anode. And then we move out to the right, and we go out basically to the end of the chamber. The red X's are the floating potential with our new probe. That means you stick a probe in there, it's going to raise up to a certain electrical potential on its own just from being inserted in the plasma. We measure that, we move it out, and we take measurements. That's the red line. And you can see that it goes from 300 volts down to 0. Totally makes sense. We had our anode at 300 volts. You move the probe all the way out to the end of the chamber, it goes down to 0. Then the fun starts. And you can calculate other parameters in the plasma, like the electric field strength. Okay, so electric field strength is how much your electrical potential changes with distance. And so if I had a chamber that had a 300 volt anode here, and the end of the chamber, which was a meter away, went down to 0, you would say that the change in electric potential is 300 volts per meter. Okay, that's how you describe electric field. 300 volts per meter is the change. But what we found very clearly from this data, and I'm sorry I didn't label the vertical axis better, but that green peak, that's the electric field. That peak has nothing to do with those numbers on the left. That green peak is at about 8,000 volts per meter, not 300 volts per meter, which you might think if you just looked at the rough numbers. So this is great because it's showing us that these discharged plasmas, they have the ability to sustain within them much more intense regimes, much more intense things going on than you would ever guess if you just were stepping back and looking at your power supply, right? If you look at your power supply, you would never guess that there was 8,000 volt per meter electric fields in there. The black line is charge density, so these double layers exist because charges, positive and negative charges, build up next to each other, so we can see we're starting to be able to measure those charge density fluctuations. At the left-hand side there, the black line, when it gets a little bit closer to the anode, it drops way, way down. I didn't include it on this graph. I couldn't get that on there, but just so you know, that black line drops way down as you get one fraction of a millimeter closer to the anode. And then the blue one is the resistance of the chamber. So since we have designed a double probe also, we didn't show you that one, we can stick those 2 wires in there and measure the resistance of the plasma across that little gap between the 2 wires. And so you can see the resistance is basically infinite as you get closer to the anode, drops to almost 0, climbs back up, falls back down, and that last rise at the end there of the resistance line, I'm pretty sure is heading back up to essentially, huge, huge numbers. I love this graph. I'm very proud that we were able to make this because you don't often see so many plasma parameters, all taken together and displayed together. And similar to what I was saying about the overall plasma electrical characteristics is so needed for astronomy so you can start making circuit diagrams. This sort of ability to see all these different parameters in the plasma at the same time on the same graph is what we need in order to start digging into what's going on, what's the physics inside of this plasma here. And since a lot of these results were done pretty recently, more analysis kept coming in. The day we were supposed to submit it, Lowell gave me this graph. Okay, I'll put this in there. Before we hit send, he sends me another graph. Okay, I'll put this one in there. This is the electron temperature in the different areas of the plasma. We're getting it close to the anode. Okay, so it's going up and down, electron temperature. See how that close to the anode there is at 7? Okay, that's electron volts. 7 electron volt electrons. that's pretty hot for earthly conditions. If I had a jar of 7 electron-volt electrons, and you stuck your thermometer in there, it would read about 81,000 degrees. That would be the effective comparable temperature to it. So we have, in SAFIRE, tens of thousands of degree fluctuations in temperatures taking place over millimeters or centimeters safely. No one's being hurt, right? Not yet. And we can control it, we can reproduce it. And as we saw with the probes, we're starting to see how to release that energy. But we'll talk more about that very soon, about the release of the energy. Now, it's important to point out that the team does have a paper published from previous work. This was written by Lowell Morgan and Montgomery Childs. It was published in the Plasma Sources Science and Technology Journal. This looked at previous discharges mostly from the point of view of how much light was being emitted. So really good analysis by Lowell on this one. One of the main conclusions from this was we're trying to answer, how do these double layers form? Believe it or not, no one really knows how these double layers form, okay? It's pretty interesting. Lowell's idea was that the production of negative ions and electrons creates instabilities in the plasma, which leads then to the segregation of the charges. If you want, we can certainly get you this paper that you can dig into his analysis on that. And again, to remind people, I'm excited by some of our results because we're seeing now, again, fluctuations in these parameters that are comparable to the sort of fluctuations we need to have to be say, yes, we're looking at astronomical quantities here, comparable quantities. We should take just a breath in before getting into radiation. So everybody breathe. Yeah. Breathe out. We were talking about the ITER, tokamak experiments, and just the sheer amount of money that's going into them. And it seems like we're trying to force nature to do something it doesn't want to do with these magnetic confinement fusion experiments. And, you put another $50 million into it, and then you get much stronger magnetic fields to try, and it still just doesn't work. You can't make the plasma do it. And I don't know if you can see it from the videos, but when we're in the lab working on this plasma, we're not actually driving it so hard. We're not forcing nature to do anything. That's certainly how I feel it. It's all. It seems like we turn a dial, and then the plasma responds, and it's everybody's happy. We're not forcing anybody to do anything, right? So I feel like that's one of the things that it feels to me like we're on the right track, because it doesn't have that feeling of forcing something that nature doesn't want to do. Plasmas are certainly Dr. Morgan's specialty. We said, could you please take a look at this? Take a look at what happened to our tungsten probe, okay? From what you know, can you please dig into this? So we spent some time looking at that. Radiation trapping, so we're going to talk about that really soon, how to envision that. So I knew that biology had complicated chemistry, right? Biochemistry, it's complicated stuff, right? Life has all these things. And I'm starting to realize plasma chemistry is really also equally complicated. And it makes me wonder about what sort of chemistry is being done, on stars. It's complicated stuff. So Lowell came back with, this is not a result of thermodynamics, traditional thermodynamics that melted this probe. You have to look at radiation hydrodynamics, which he explained to us is really one of the most complicated areas in applied physics. There's not much that you could say is more complicated. It's why Livermore and Los Alamos labs always have the best computers, okay? Because you need supercomputers to do these analyses. And I wrote down this quote from him, that nuclear weapons have very little to do with nuclear physics and a lot to do with radiation hydrodynamics. Okay, let's talk about radiation trapping and the slowing of the speed of light. So imagine that this whole room is the SAFIRE chamber, okay? The stage is the anode, and all of us are hydrogen atoms, okay? And being hydrogen atoms, like we said, that every species of bird has its own song, so we can all talk to each other if we're all hydrogen atoms. We can exchange thoughts and tell each other things and exchange photons and energy, stuff like that. And the anode's up here, and electrical energy is being pushed out to all of us from the stage here. Okay, so you got the picture, right? Now imagine that whole side of the room gets, you're now all helium atoms, okay? To the rest of us, that side of the room just went dark. We can't see them anymore, we can't hear them anymore, because we are now on different wavelengths. We cannot exchange energy with them anymore. Okay, so we'll leave them for a second, we'll just focus on this side. Electrical energy comes off of the stage. And let's imagine that it gets absorbed by two people in the front row, okay? They hold on to it for a while. They get excited. They're bubbly. They can't sit still in their seats. They're getting all kind of pumped up. But they hold on to the energy. They hold on to the excitement for a while, maybe 30 seconds, okay? While they're holding on to it, two more people in the front row get some of this energy. They get all excited. Can't sit in their seats. They want to tell somebody something. After about 30 seconds, those first two people finally can turn around and they communicate their excitement to somebody behind them. But then that person who gets that excitement behind them in the second row, they also have to hold on to it for a while. They can't just turn around and tell the person behind them. So there's this slow progression of this excitement. Okay? If it were a different scenario, if you weren't hydrogen and I wasn't communicating to you this specific frequency of light, which I'll mention soon, then as soon as you got excited, you would just turn around and talk to the person behind you. As soon as they would just turn around and tell the next person behind them, and that excitement would go out through the hall at the speed of light, right out. But that's not what happens. There's a specific resonant frequency that hydrogen has. It's 122 nanometers. That's pretty hot stuff. Okay, that's the level of energy that we see coming off of solar flares, coronal loops, things like that. That's how we see that level of intensity. When hydrogen gets that, it holds on to it for a while. In fact, it holds on to it thousands of times longer than it takes to just exchange the information with another hydrogen atom. So it's that particular way that hydrogen manifests that slows down the speed of light, the progression of light, by thousands of times, and ends up building a huge amount of energy in that region. We didn't forget about the heliums. Okay, so the heliums, they don't see anything going on over here. It's dark, they can't hear anything. One of you gets the bright idea, let's build a probe. And we'll put it across the aisle and we'll see. So it's like a couple of guys go running back to the breakout room, they take apart some of Ricky's paintings, they get the wood frames, they stick some dried sage that I saw over there on the table in that, and two guys put the probe across the center aisle, and it touches into that region and bursts into flames. Ashes fall on the floor. So that's how they know that, look, we couldn't see it, it wasn't visible to us, but as soon as we put our probe in there, it got fried. That's radiation trapping and slowing down the speed of light. That's what we have going on in our chamber. And that's my, now you know all about radiation hydrodynamics that you need to know. You're How'd I do, Lowell? Was that okay? Okay. Yeah, and you know, what's interesting also is that this whole thing, this whole arrangement is, you could call it electrostatic, right? We just have a battery, right? We just have 300 volts, so it's an electrostatic machine we have. So we have an electrostatic machine that can trap photons, high energy photons. We have an electrostatic machine that can slow down the speed of light. We have an electrostatic machine that can release in an instant very large quantities of energy. And it's all, again, done, we're controlling it. We can predict how to get to these regimes. This is a plot of the expected temperature the probe tip would get to. And so you can see under certain regimes, which are the left and right axes there of hydrogen density and electron temperature. The red area there, 10,000 degrees predicted. When that poor probe goes into the hydrogen section, you could expect that much energy to go into the probe, raising it to about 10,000 degrees. Now, does that explain everything we saw? I don't know, but it certainly is the right way to start analyzing this problem.
A lot going on this year, and we were really getting concerned towards the end of the project whether or not we're even going to do this. We started getting the analysis back, and we started getting really excited. There was actually hope. Even so, thermodynamics can't resolve for these things. Radiation and hydrodynamics can, plus a lot of other things. So we see ourselves as, now that SAFIRE, I would say, is stable. We can get these stable plasmas. We're now in a place where I would say, with pretty good confidence, that we can start to actually do a number of experiments and get really good data back. But these results are, in my view, spectacular. And the chemistry changes. Don't know. We shouldn't have barium in there, or titanium. No idea where this stuff came from. We can be guessing, but we should find out. Variations in electron density comparable to the photosphere, heliosphere, and nuclear bombs. Those are the only places that we see these kinds of intense, dense plasmas. Electrical confinement of high-energy photons. That's a lot. And what we're saying here, in effect, is that what Michael was talking about, and the transformation characteristics of the plasma, the double layers, those double layers, when Paul's talking about second-order interactions, what we're talking about is like an audio feedback loop that just keeps getting bigger and bigger, except that in a double layer, it gets to a point, the double layer forms, and the plasma now becomes stable. Up to that point, it's electrically, you can see a lot of activity, but when the double layer forms, it goes stable, and it's very robust. So it'd be like the double layer, and I'm going to jump out here a little bit too, because I think we're really at that place where we have our atmosphere on the Earth, 350 miles up. Conventional science says, well, it's gravity that holds our atmosphere here. But mechanical engineering, I mean, we have big machines try to contain or get vacuums that aren't even close to space vacuums. What I'm trying to say, in effect, is that only 300-mile distance, we've got a space vacuum that can suck your eyeballs out of your house. I mean, out of your head, out of your house. Long day. Out of your head, and yet there's no mechanical device retaining our atmosphere. And what we are seeing, what we forgot to mention actually, is we do have a pressure delta in SAFIRE. And that's a big deal, because I think Langmuir predicted theoretically that we should see this. I mean, this is what Lowell's... Right. Right. What we're saying, in effect, is that when we get a vacuum in the chamber, a gas would fill this room, where the chamber and the pressure in itself would be equal throughout the chamber. But when these double layers form, that's not what's happening. So we do actually have higher pressure inside these double layers than we do actually have outside in the greater part of the chamber. So you actually have a plasma force field that actually can contain these molecules, these gases. This is a big deal. So the core of SAFIRE is cooler. The highest temperatures we saw was maybe around 1,000 degrees Celsius. And obviously the temperatures, or the effective temperature, or you might say the response temperatures we're getting with the probes, are many orders above that. Way, way, way above that. So these are the things that we're exploring with SAFIRE, and I think that's really it. These questions we're going to leave on the screen here, and I guess we're open for questions and answers.
Other way?
Yeah. 1 millimeter, 10. Too much, back. That's good. Okay.
So the temperature of the anode right now under hydrogen is 600?
It's been at 600 even when we had like
That's good.
kilowatts going through there.
That's good, that's good.
It's a lot hotter with
Whoa, there it is. There it is.
Shortly after the 2017 Phoenix conference, the SAFIRE team discovered a unique process that initiates and sustains the plasma double layers.
Look at the UV.
This was a major discovery because it is these plasma double layers that produce both the extraordinarily high energy densities and the electric field that contains these energies within the plasma. This new advancement in plasma science demonstrates a process that consistently creates, contains, and controls the plasma double layers in stable exothermic plasma reactions. Although the energies and densities are comparable to the sun's photosphere and nuclear bombs, the data shows no harmful side effects such as radioactivity. But the science of what is actually happening at the molecular and atomic levels is not yet fully understood.
Color changing? Oh, for sure. That's different than the last time.
And this is when the tendricles were coming out?
Understanding these reactions will give valuable insight into the way the sun's atmosphere functions
Double layers be set up.
I want to get agreement as to, okay.
and provide the foundation by which these energies can be beneficially harnessed. This research will be the top priority of 2018.